Hey guys, we are going to be doing some old stuff and introducing something new, which is talking about systems of linear equations this week. So in this little lesson, we'll just do a couple equation solving practice, and we'll do systems of linear equations two ways, one by graphing and one by substitution. This should be what you are learning in your algebra class. Hopefully this gives you some extra context and helps you understand what it is that you're doing in that class. So let's start with some equation solving practice. Here's a similar type of problem that we've seen over the last couple of weeks. So we want to solve this. Negative 23 equals 3x plus 9 minus 11x. So you'll see right away that we have two cases of x, and so we need to combine those like terms. So we do 3x minus 11x gives us negative 8x, everything else stays the same. Now we need to combine like terms and get all the numbers to the other side. Since we already have our negative 8x over here, let's subtract 9 on both sides to get it over with the negative 23. So taking 9 away from both sides, we get negative 32 equals negative 8x. And then we just need to get x all alone. So we simply divide both sides by negative 8. Looks like this. The negative 8's cancel, and we get x equals 4. Sorry, this should be a negative 8 on the bottom, not a negative 32. That's just a typo. Sorry about that. We're just dividing both sides by negative 8. All right, on to the next one. Okay, next we have 23 plus 18x equals negative 21 plus 14x. So here you can see we have two cases of x again, but now they are on opposite sides of the equal sign, so we're going to have to combine like terms across the equal sign. So it doesn't make it that much more difficult, we got to do in this particular way. So we're going to, well, I've elected to subtract 14x on both sides. That's going to cancel my 14x on this side, and it will move all the x's over to the left side. So 18x minus 14x gives us 4x, and then we still have the 23 and the negative 21. Now, since our 4x is over here, let's get this 23 out of there. Remember, we want to combine like terms and get all the numbers on the right-hand side in this case. So we'll subtract 23 on both sides. We have 4x equals negative 44, and then of course we need to divide both sides by 4 so that we get x by itself. So dividing both sides by 4, and we get x equals negative 11. There you go. All right. So next, we're going to talk about systems of linear equations. So let's just say, for example, we're given two equations, and the problem that you might see on ALEKS will say find their solution graphically. There's a bunch of ways to think about this, but the one that makes the most sense to me is to think of each of these lines like a straight street that's running through the city, and we want to think about where they intersect. So this is really important. We're going to talk about this a bunch, but the solution to this system of two linear equations is wherever they cross. So it's just like if you have a street and they cross. I'll show you that in just a moment. So for example, here I have plotted the first graph, y equals 1/2 x plus 3. You guys know how to plot that. I've done it for you in Desmos, which is just a program online. The next one we'll plot, which is y equals 3/2 x plus 1. It's plotted like this, and notice they cross at exactly 1 point, just like you could imagine two streets crossing. I'll show you that in a moment. Now, the answer to what is the solution to a system of linear equations should always be an ordered pair. That's really important to know. You're going to have an x and a y coordinate of that solution. So if you can graph easily those two lines, it's very easy to find the solution because it's just where they cross. So the solution is 2, 4. Okay. Now, here I just took a screenshot of Google Maps near Riverside. All of these streets cross at exactly one location. So if you think of those streets as like a line that we've graphed, they will cross at exactly 1 point. So you can see here West 29th Street and North White River Parkway East Drive, that's a mouthful, cross at exactly a single point. So if we had a grid paper here, we could give the coordinate, the XY coordinates of that spot. Same here, the same West 29th Street crosses East Riverside Drive at exactly 1 point. Okay. Now there are three different kinds of systems that we can have. They will either have one solution, infinitely many solutions, or no solutions, and we'll look at each case. Here's the one that we just talked about. You'll see questions just like this on your ALEKS. So you'll have two lines intersecting. You'll notice there, this will be important in a moment, that they're labeled L1 and L2 for line 1 and line 2. Now this one is simple enough. You're just going to click that button there that says it has exactly one solution, because you notice they cross at one point. And then importantly, they cross at one exact point, and importantly, we'll write it as an ordered pair. That will be our solution. So we'll check that box. It says it has exactly one solution, and then you can see there the x-coordinate is 2, the y-coordinate is -1. So that's what you'd type in on ALEKS. Now another type of system you might see is one just like this. So you have the two lines. Notice that those lines are parallel to one another. They actually have the same slope as one another, just different y-intercepts. And so these two lines will never, ever, 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 ever cross, which means that to ask what is the solution is kind of silly. It has no solution. So since the lines never cross, we'll check the box that says the system has no solution. Finally, this one looks a little weird. It looks like there's only one line drawn. It turns out that both of these lines, if you solve this and put it into slope-intercept form, these are identical lines, which means that at every instance, every moment, those lines are crossing, which means, well, technically speaking, there are infinitely many solutions because the lines are the same. That means that they cross everywhere. So the only way that you can get lines that never cross is if they're parallel, and the only way you can get lines that have infinitely many solutions is if they are the exact same line. Now you'll notice that these two lines are written differently, but if you put the second line into slope-intercept form, you will find that it is the exact same line. I will let you try that to verify. Okay. So once again, check the box there that says there are infinitely many solutions, because they are overlapping absolutely everywhere. Now let's do a real-life example of this. So I kind of broadened my search here. You can actually see both Riverside and Heron are on this part of the map. You can see a couple other high schools too. And can you find some examples of places where streets cross once, where they don't cross, and where there are infinitely many? Okay, so first, I'll try to highlight these here. MLK Drive, or street, crosses with East 30th Street in exactly one location. And again, if this was a grid map, we could actually give that an XY coordinate. That is one place where they cross exactly once. You can think of literally hundreds of other places where streets cross exactly once on this map. Okay, what about streets that never cross? Streets that are, let's say, parallel to one another. So I found East 16th. Take a moment, visually see, are there any streets nearby that it doesn't cross? I can see one right there, 22nd Street. Those two streets are never ever going to cross. Now, one difference about what I'm showing you is that, of course, these streets don't go on forever, whereas lines do go on forever. The last one, so that was 16th and 22nd, they never cross. They are parallel to one another. The last one here is a little bit of a trick. Is there type of road, or is the road in this map two roads that cross everywhere that would have infinitely many solutions to the question? And actually kind of a trick question, but the answer is yes. North Meridian Street, back in the day, used to be US 31, and actually when you go up north on Meridian, it eventually turns into US 31. So this is a bit of a trick question, but you can see I've highlighted it in green and then basically overlapped it with a second line also in green. So technically, Meridian Street and Old US 31, even though they're called different things, they're the same line. They cross everywhere. So it's okay to say that if you're on Meridian, you are on Old US 31. All right, on to a similar but different type of question. Here we're given a bunch of solutions, ordered pairs, and our goal is to check to see if it's a solution to this system of equations. Basically, for it to be a solution, it needs to make both of these equations true. Let me show you what I mean. So if we plug this first point into the first equation, so I'm going to plug 3 in for x and -4 in for y. And then I'll just do the arithmetic. So 5 times 3 is 15. 5 times -4, that equals -16. That equals -1. If you do the arithmetic on this side, you have 15 minus 16, that's -1, equals -1. Well, that is a true statement, which means that we're on our way. This might be a solution. Let's plug that same thing into the second equation in our set of equations here. So when we do that, we plug it in, and we get 3 times 3, which is 9. And we get -2 times -4, which is +8. Adding those together, we get 17. And all along the way here, we've got -5. Does 17 equal -5? It definitely does not. So this is not true, which means that, unfortunately, we have to rule this out as a solution. So no 3 comma 4 is not a solution. In other words, that is not where those two lines cross on a graph. Okay, now I'll speed this up. I'll just show you all of the solutions. So we already know that the first one is not a solution. In the second case, if you plug it in, I'll let you pause if you need to and just verify these. But if you plug it in, you get the first one's false, the second one is true, which means it does not count. Okay, the next one, the first one's true, the second one's true, which means that yes, indeed, it is a solution. So kind of by default, we know this last one can't be true, but we'll check it anyway, and you'll notice that they're actually both false statements. So the answer to this question is that -1, 1 is a solution, and none of the other ones are solutions. You could, if you were so inclined, verify that on Desmos by graphing it or graphing it by hand, and they should cross at exactly -1, 1. Okay, let's try another method for solving a system using substitution. So, for example, here we've got two equations. Now you'll notice that one of them is already solved for a variable. That's really convenient. That's the only type you're going to see today. But this one is already solved for y, and we have these two equations. Now, if you look, and we start right here with the top one, y equals 2x minus 12, well, it has both x and y, so we can't get either x or y alone. We can't find our solution. So it can't be solved. It can't be solved. The way to think about this is that the variable y represents all of this stuff, 2x minus 12. So where we see y show up in a different place, so this is the same y, we can just straight up replace it with what y is equal to, which is this expression 2x minus 12. So I'm going to expand this out. I'm going to substitute, which is the name of the game here. I'm substituting this thing in red right here in place of y because they're equal to one another. So I remember conceptually this being kind of difficult for me to understand that this letter actually represents all of this stuff. So hopefully we'll do a couple practice and you'll start to get comfortable with it. From here, notice that there are only x's and numbers in this equation, so we can solve this just like a normal equation. So the first thing we do is distribute. 4 times 2x, that's 8x. 4 times -12, that's -48. And then we can combine like terms. I'm going to go kind of quickly here. And then we can add 48 to both sides. Dividing both sides by 11, we get x equals 5. Now, really important, we are not done yet. Remember, each system of equations crosses at exactly one point, which is an ordered pair. So we found the x coordinate. Let's plug that x in and find the y coordinate. So it's really important to stop yourself when you're solving systems. We are not done yet. We've just got the x coordinate. So let's plug that back in. So we're in place of x, we're now going to substitute 5. So 2 times 5, that's 10, minus 12. That's y equals -2. So after all of that work, our answer is the x coordinate followed by the y coordinate. That's 5, -2. And that's what you would type in on ALEKS. Let's do a quick check graphically. These are the same equations from just a moment ago. Just to verify, they should cross at exactly 5, -2. I've got the first equation plotted. We'll plot the second one, and lo and behold, there it is. It crosses right at 5, -2. So in a bunch of ways, you can solve systems either graphically or with substitution. In many cases, for a variety of reasons, graphing might be impractical. For example, you don't have graph paper at home. And so sometimes doing it by substitution is going to make our lives a lot easier. Okay. If you'd like to try this, by the way, just to check your answers, you can use the graphing calculator at desmos.com. All right, we're going to fly through one more example. So in this example, we've got 2x plus 11, and then we have the second equation. We're going to sub in what y equals from the first equation into the second one. So in place of y, we're going to write what y equals, which is 2x plus 11. So substituting and then distributing. So I've substituted in for y, 2x plus 11, and then I just go ahead and solve this like a regular equation. So distribute, and I have 5x plus 8x plus 44 equals 5. I combine my like terms, so 13x plus 44 equals 5, and then I solve, I get x equals -3. Remember, not done yet. We have to plug that in. Y equals 2x plus 11, plugging in -3, we get y equals 5. So our final answer would be -3, 5. Very quickly, graphically checking that. Indeed, they do cross right at -3, 5. Thanks for watching, guys.